Hi, this is James Douma. I'm being brought to you today by Dave Lee's channel. We're doing an impromptu chat about some recent developments in FSD stuff. And the topics we're going to cover today are the Starlink announcement with T-Mobile last night, the release notes for 10.69, and we're going to talk a little bit about Ashok Elluswamy's CVPR talk.
Awesome. Yeah, thanks everyone for joining in. I asked James to do the intro because I'm actually in my car near Mount Rushmore, and it's kind of hard to handle all of the recording and the note taking or just viewing the notes and everything. So thanks, James. Yeah, this is awesome, man. I wanted to talk to you actually about Starlink because I thought that was an awesome announcement last night. But before we do that, the big news this past week, Tesla stock split 3-1. How does it feel having 3 times the Tesla shares that you had just a few days ago?
I preferred it when it was 5 times, I was looking forward to 10 or 20, like that would have been great. Yeah, we're not getting the 10 or 20. So 3 is good. That's good. Yeah. Stock splits are, they're happy making things. It's easier. It's certainly a lot easier to get family members, excited about buying something where they don't have to sell a car to get a share, right? So.
Yeah, yeah, exactly. Tesla stock split. It feels. I don't know. It's gonna take me a few days to get used to those numbers because I have to translate it times 3, to see what the stock price was before. But I'm sure by next week, I'm sure everyone will be totally fine with the new stock price.
I had to go through all my spreadsheets and all my models and whatnot and change all the formulas.
That's right.
I haven't done the big models yet, so those are going to be a hassle because it's the numbers are all in Python code scattered around. But yeah, we'll see.
Got it. So Starlink T-Mobile announcement. So last night, Elon was previewing it, saying it's going to be a big announcement. I thought it was going to be something like just improving T-Mobile's like cell towers, especially in remote areas where they would add a Starlink connection, make better, like add new towers where they didn't have towers, just improve it. But this totally, sideswiped me or blind spotted me. It's just
I'm super surprised. Yeah. I was sure that backhaul was going to be the thing because backhaul for filling in the gaps is such an important thing. And as a lot of people have said, Tesla's got solar panels, they got power walls. You could build a cell tower in a box and slap a Starlink antenna on it, and you could put like conventional cell towers just like in the middle of nowhere, drop them from a helicopter, lower them on a mountaintop, bolt them down. And I was expecting some, clever, innovative, aggressive thing along those lines. And what we got was completely different. Like I wasn't expecting cell towers, regular cell phones to satellites. That's hard to do. Like that was not on my bingo card.
Yeah.
Definitely.
I mean, it just feel like it skipped a couple, I don't want to say generations or technologies where it's like, forget the cell towers, go directly to the satellite. So I wanted to ask you what do you know about this? How difficult is it to, for a satellite in low Earth orbit to actually connect to a cell phone? Well, yeah.
500 kilometers.
Yeah. But what are some of the challenges, that you think Starlink is having to overcome here?
The cell phones are not designed to talk to a tower 500 miles away. They're just not, right? I mean, usually when you build a communication system, you split the load as much as you can between the 2 different ends of the communication system, right? So if you want to talk a long way, you split the burden of the antenna and the power and the processing sophistication kind of between the 2 ends. And that kind of makes the system sort of more tractable to do. But now we have these cell phones that are designed to talk to cell towers, that are maybe a few miles away, maybe 15 miles away or something like that. And they have, a few hundred milliwatts of transmit power. And they have pretty sophisticated processing for modulation techniques and that kind of stuff. But they don't have nearly the level of sort of dealing with artifacts and stuff that you might want when you're dealing with an antenna that's like 500 miles away and is moving really, really fast. So the satellite has to take on all that burden, right? Which is why they're putting like a 5-meter antenna on the satellite just for dealing with this. And even then, they're only going to get, I think, Elon said 2 to 4 megabits or 1 to 2 megabits.
Yeah, 2 to 4 megabits. Yeah.
Yeah, 2 to 4 megabits in a cell. So I mean, it's just really, really hard. But the flip side is any amount. I mean, text messages are small. Messaging is super, super low bandwidth. So like any amount of connectivity that you can get to these places where there's just none at all right now is incredibly useful to people, right? So it's this interesting place. They have to throw a lot of technology and a lot of expense at being able to provide incredibly, what we're used to today, because, cell phones are fast and internet is fast. And what seems like a really small amount of communication ability, but it's so useful if you're in the middle of nowhere, if you have an emergency, right, or you're just, on a cruise ship someplace. And, even being able to carry on a text message conversation is way better than not having any contact at all for an extended period of time.
Yeah. I think I've been following kind of these satellite phone trends for the past few decades. I remember in my 20s, I was traveling to all these different countries, and I carried like a sat phone just to be able to make calls and stuff. But I think before this, like Iridium, the satellite network, was probably the I don't say the only option, but the best option to just do emergency text messaging when you're like hiking somewhere or mountain climbing somewhere. But it's extremely expensive. You have to have a separate device. It's just impractical for almost anyone to really, buy that stuff unless you're a professional like expedition person. But this opens up kind of like basically emergency calling to almost anyone, anywhere. It just is a huge jump.
In emergencies, when you have a natural disaster, to have like a minimal backup that's guaranteed to work for the cell system, man, that is so incredibly. This is going to profoundly change, emergency services in the world when it gets distributed, because the assumption that you can just reach people is just different, right? I mean, here's the thing, right? Apple Watch, this thing has a cell transceiver in it, right? Mm-hmm. It's like all these people who've got the version of the Apple Watch that has a cell phone in it. You are never, ever, ever going to be out of contact, right? Yeah. If you got your watch on in an emergency, no matter where you are on Earth, and Apple, they have the features on the thing where, like, if you have an accident, if you fall down, the watch can detect it and automatically call for help, right? Like, that's just totally next generation level of sort of accident preparedness, for the communication system.
Yeah. So in terms of like how they're doing it, it seems like they're just using some current cell phone bandwidth, right? And then it seems like the heavy lifting is all done by Starlink, right? The satellite, where it's going to, basically broadcast or listen in and send out everything to the cell phones. So, I mean, I'm guessing what's your take on the partnership with T-Mobile? Are they doing that because Starlink isn't commissioned to be a cell phone provider, so they need to work with an existing, you think, cell phone?
Probably the most important. I mean, certainly like billing and that kind of stuff, handling that thing, like having a partner that's already got all that infrastructure is a good thing. I don't know, maybe that SpaceX wants to go into the cell phone business, right? Which is why I thought backhaul was the natural fit for them. But they need a chunk of spectrum that they can access, and ideally, you'd like contiguous spectrum, where a lot of cellular bands are broken up regionally in the United States, so that a provider, they have this frequency here and that frequency there, other frequency over here, to make the first version as reasonable as possible. If you had like a band that some cellular provider owned, like over a really large area, ideally over the United States, because that's a good place to start to start your service. And T-Mobile has a PCS band, which is, so PCS is the set of frequencies between 1850 and 1990 or something megahertz. It was the first digital cell phone band, but I think it stands for, the FCC brands them as personal communication system frequencies. It's a good band to use for this kind of stuff, just like its physical characteristics are good. And T-Mobile has a slice of that where they have 100% coverage everywhere in the US. So by partnering with T-Mobile, one thing that SpaceX gets is they get it, for their first go, they get a single frequency that they can just use everywhere.
Got it. Interesting. Do you think Verizon, AT&T will join in somehow on this, or do you think for the time being it'll just be a T-Mobile thing with SpaceX?
The way that they were talking about it last night. I get the impression that SpaceX is not going to be excited about the idea of trying to do a single carrier, to provide exclusivity. That's obviously attractive from the carrier end of things, right? But and traditionally, that's what you'd expect carriers to do. You'd expect a carrier to want to get something that they could lock other carriers out of to make for an upsell. Because I can tell you, man, if AT&T doesn't do it, I'm moving to T-Mobile. Right? I really. To me, this is like, it's a very significant feature to have, emergency connectivity, even though I'm never going to use it. But to me, it's like having a hospital, like in the town I live in. Like, I don't intend to use it, but I want it there. Right? So,
interesting.
I think a partnership is a great way to go. And I think other carriers will probably be persuaded. And in the short run, there could be this technical limitation of how many different frequencies and how frequency agile the satellite is and how big the cell sizes are. And like, I haven't actually looked at the frequency maps. I think they're mostly regional. Like, there are places where, different providers own different chunks of spectrum in like metropolitan area size chunks. And that could be tough for Starlink, because at least right now the cells are like 15 miles across. So they can't distinguish things that are smaller than that.
Yeah. It reminds me back in the day when the iPhone launched and it was just AT&T exclusive. And AT&T got all this marketing benefit of being the only carrier with iPhone. And, Apple got, a cut of all that, and it worked out. But I mean, it probably lasted a bit too long, but I would imagine like the T-Mobile partnership, maybe there's a time limit, like 3 years or 5 years or something, where it could be exclusive, and then it opens up where SpaceX does partnerships with AT&T and Verizon after a few years. But we'll see.
The way they were talking, that the T-Mobile CEO was talking about it last night, it kind of sounds like there's no exclusivity, like contractual exclusivity, and I don't his approach of wanting to use it as kind of a way to get to mutual roaming agreements, to like, that like the pull for T-Mobile would be to get cross roaming agreements, especially overseas. Because one of the things that T-Mobile has that other carriers don't really have right now is they give you kind of free international roaming. Like, that's a seller for them. And I suspect they they attract a significant number of customers whom that's important to. Because, I mean, I don't know if you use AT&T or Verizon, but you travel internationally, you get robbed. Right? I mean, if you care about the cost of those services.
I think Verizon's like $100 a month just to go international roaming with your data, and they only give you 5 gigabytes or something. T-Mobile just gives it, I think, for free.
It's pretty expensive on AT&T.
I'm actually headed to Mexico maybe in a few weeks. I want to take my kids to Mexico City to check it out. Should be fun. When the T-Mobile announcement happened, I was like, if a phone can connect to a satellite, Starlink satellite, then surely a Tesla car could do that too. Because aren't they just basically putting a phone or the components into a Tesla?
No, the existing cars,
cellular remote, antenna, all that stuff. So I'm like, this is probably going to happen. So, and then Elon confirmed that, by replying saying yes. But do you think? So you're thinking that the current Tesla cars will be able to handle? Do they have the right spectrum?
No, it's. I mean, if you have a cell phone. I mean, they didn't say what modulation scheme they were going to go with, so we don't know if it's like 2, 3, 4G, whatever that they're doing. It may, it would be interesting to know that, but they did say something along the lines of like any phone manufactured in the last few years or whatnot. So maybe it's a 3G modulation scheme that they're using. So, and 3G maybe not, because 3G is it's getting eliminated in terrestrial networks right now. But I would guess that certainly if you have a recent model, it's got a cellular transceiver in it, right?
Exactly. Yeah. I mean, to me, that's a decent selling point, actually. Wherever your Tesla is, you're always going to be able to call or text for emergency.
Yeah. But OnStar will have this too. Other car carriers, like any car carrier that wants to use that feature, they can do it.
Okay. Would they connect with T-Mobile, or, I mean, because if T-Mobile has that agreement, I mean,
I mean, they would need to have a contract with a carrier that had a contract with SpaceX, right? Because they have to be able to communicate on the frequency that the satellites are able to use. Yeah. And whoever owns that band of frequency, they have to both cut a deal with SpaceX and cut a deal with, you know, whoever the end customer is that's going to use it. So right now, if that's T-Mobile, then yeah, you know, if T-Mobile is the only carrier who's got a piece of spectrum that Starlink is allowed to use, then to get access to that spectrum, you have to get T-Mobile's permission. So normally you'd get a contract with T-Mobile.
Yeah. All right. So I want to go into Tesla FSD Beta 10.69. So I wanted to talk with you about this because my general sense is that, you know, most people aren't understanding like what's improving in 10.69 and how significant some of the improvements are. And so let's take a step back and approach it through different ways. So I wanted to ask you about Chuck Cook's unprotected left turns, maybe go into Ashok's presentation, who's the head of Autopilot, who gave a recent presentation, and then also go into the release notes to kind of decode for the people out there, like exactly what the improvements are. But first to Chuck Cook's unprotected left turns. Did you see any of his recent videos with 10.69?
Yeah. Oh, yeah.
You did?
Yeah.
Okay. What struck me personally was like some of the movements into the median and then from the median out, they were just like, I mean, this is night and day compared to 6 months ago, you know? I mean, it's a completely different, you know, beast.
I've been watching Chuck's left turn videos from you know, since he started doing them, and I have you know, I've thought a lot about like what things have to get better. Because it was never like one thing. It's because you know, being able to make a left turn, it's built on other fundamental capabilities, right? Being able to predict things, being able to sense things, you know, being able to do planning of a certain level of complexity with certain features in it. And I was, you know, I was not expecting them to like get Chuck's turn in this time frame. That it's an impressive movement forward. I mean, when I was a lot of things got a lot.
Yeah, better. Exactly. I'm not like, completely like, you know, technical, understand everything. But when I looked at those turns, I'm like, I don't think most people are getting how complex it is to be able to do this. Like you have to basically, you know, be really accurate with all the lanes, with all the objects, with all the velocities. You know, you need to have predictions, you know, of where everything's going to be at, you know, and if anything is off, you know, like it could be extremely dangerous. You can basically get killed.
And it's important. They didn't solve Chuck's turn. They solved Chuck's style turns, right? It's to solve that whole category of turns. There's a bunch of things because like on Chuck's turn, the visibility, it's not great, but it's not terrible. But there are other turns that are really similar to that and have much worse visibility. And the visibility is bad for different reasons, depending on how the road is approaching you and what the lighting is, what the foliage is on both sides, whether or not there are buildings casting shadows and that kind of stuff. You know, the effective visibility you have changes. And occlusions are super important, right? Near field occlusions, poles, mailboxes, trees that are in the foreground that you have to, like Chuck's turn kind of demonstrates this class of things where there are, you know, parked cars or something near you and you have to look through them or look behind them and sort of understand the traffic flow that you're seeing through the gaps in these things that are blocking your field of view. And that is not a simple problem to solve in a general way. Like for any given turn, you can sit down, write some code and say, here's a good way to do it in this situation. And this is actually something that Ashok mentioned in his talk, which I didn't get until I went back and looked at it a second time, I mean, my sense, he doesn't say explicitly what they're doing, but he talks about reasoning about occlusions. So instead of like, if you wouldn't talk about it you wouldn't say reasoning about occlusions. If the approach the company was taking was on a case by case basis, you know, like a routine for if I have one tree in the foreground, if I have a bush in the foreground, here's a routine for if there are cars in the foreground, blah, blah, blah. You really want something that has a sense of the fields of visibility and what that's doing in a general way to your ability to ascertain the flow of traffic. And then the reasoning part is if it's not good enough, like, you know, to what degree can you see things? And if you can't see things to the degree you need to, like what needs to change to make it better? And what do you need to do to to move forward, to move backwards, left, right? Do you have to inch out into traffic? Or, is this one of those ones where you just say, you tell the driver, I can't do this, right? I'm not going to.
Yeah. Yeah. It reminds me a bit about when we were driving. I think this was back in the last summer, when we met up near Corona or something. And we, after driving about an hour, we stopped and you were sharing this idea. I still remember where you're saying, Tesla could make it feel a lot better in a lot of situations by just increasing the aggressiveness, right, of the driving. But then that would make it less safe in certain situations because it wouldn't be, it's just doing it because it's forcing it to do it in a way. But when I look at Chuck's turn, it's not a simple matter where you just increase the aggressiveness, because that is a super dangerous situation. If you just increase the aggressiveness, you're gonna have some crazy crashes and repercussions. What they've done is it's not just a simple thing where they're just hacking it just for Chuck's turn, that one specific turn. They're actually having to make probably just so many fundamental improvements in how it perceives, everything, the movements, predictions, the space and everything, just to be able to make that. And I think that's the missing story with what's going on with FSD, is how much Tesla in just the past year has improved so many things about, the neural networks and their approaches. What's your kind of take on kind of some of that stuff? Yeah,
it's a lot of, there's this thing that I'd always looked at Chuck's turn as so, when your perceptions are in camera plane, right? That's what you see. You see, this, and your brain has to flip that into, like, when you look at a median that's out on a road, especially if the road is rising against you, from your perspective, you're kind of looking at the median edge on. So how wide is that median, right? Is it 4 feet wide or is it 8 feet wide? Because if it's 4 feet wide, you can't stop there. It's not big enough for you to do the median trick. If it's 8 feet wide, you can. Well, in the visual plane, like, what's the difference between seeing a 4 foot wide? Well, you're looking at it edge on. You got to be super accurate in terms of your sense of the space to be able to tell, looking at the edge of a median, if it's a 4 foot stop or an 8 foot stop. And this was a fundamental thing that I thought in particular about Chuck's turn, right? Is that it's not like the lane markings make it super clear it's a median in the general case. I mean, certainly if you live where Chuck lives and you drive those things all the time, you know how they mark the roads there. But in the general case, right, as I look at those, and it's not clear to me that that's a median that's intended for people to stop at. And if it's not marked that way, you have to sense the geometry accurately enough that you can make a prediction about that kind of stuff. And this is, in his case, it's not even a median where you can drive out. And if you're clunky, like if you don't get the position right, it's okay. It's not that big. It's right on the edge, right? So you would expect it to be one of those things where, if the neural network wasn't doing a really good job of the shape of the road and the geometry of that space, that it would guess wrong a significant amount of the time. And guessing wrong is bad in that kind of situation because high-speed traffic and a smooth flow kind of situation. You don't have a lot of time to get up to speed. And I mean, high-speed traffic is hurting you two ways. One is the collision consequences are really high, so it makes you want to be more conservative. But the other one is you also have less time to react. And when you do move, you have to commit, right? Because you have to get up to speed relatively quickly. And it seems like they got the perception thing down, they got the commitment thing down, they dealt with the occlusions at the edge of the road and being able to reason about occlusions and visibility. And all of those things seem like just fundamentally significant improvements to the system. And a lot of it, I think, is explainable by the stuff that Ashok talked about in his CVPR talk, where he talked about moving to. Actually, I thought that one of the most interesting hold
off on Ashok's talk for a second. I want to talk about just Chuck's turn. One more thing, and then we'll go into Ashok's thing. But with Chuck's turn thing, also what struck me is like if you're looking into the oncoming traffic, and if you're wrong about the lanes that the cars are in, for example, you think that the car is in the nearest lane to you, but it's actually in the farthest lane, closest to the median, and that could be a big mistake because the car can hit you quicker because it's in the lane that's closest to the median. So you have to be really accurate on which lane the car is in too, right? How fast it's going.
Just knowing there are 3 lanes on the other side is really hard to do.
Yeah,
I mean, you can see 3 lanes on the near side of the median, but you can't assume that means there are 3 on the other side. If you think there are 3 and there are actually 2, then then you automatically have less space to merge safely into traffic than you think you're going to.
Yeah. And it's like, I think it's hard for humans to know actually which car is in which lane sometimes, especially if there's all these cars coming. Yeah.
I totally wouldn't do that turn.
Exactly. And then, so on this other kind of idea of occlusions, if there's like a pole or something where you can't see, or it's like showing no car, right, for a little bit because there's occlusion, that's dangerous too. Because if you go because you think there's no car, but there's a car, then it's a death trap. So it's like, it seems like, Tesla has built the foundations where they've moved everything, I don't say everything, but pretty much almost everything to video now, where it's no longer just analyzing just the images alone, but it's in context of video. And then they've added on this whole prediction kind of probably engine or approach where they're able to know, and predict where the objects are going to be later on in the future, including kind of taking into consideration all the occlusions as well,
Temporary occlusion. They've dealt with temporary occlusion.
Yeah.
And they've integrated, I mean, that was, we knew that they were integrating across time, but we didn't know, how good it was working for them and what parts of the system it was working in. And it seems, and there are implications once again in Ashok's talk that kind of bring this stuff together. But generally, a thing that makes me happy, generally, there's the whole, 2 steps forward, 1 step back kind of thing where, and I've explained it in the past as like, sometimes you discover that the way you're doing something isn't getting you there. And you need to make some pretty basic changes to the system to open up new possibilities for ways of solving problems. And when you do that, you're tearing out some stuff that you've had for a while and it's complicated. It touches a lot of things. And so you get all these bugs. And that's the 1 step backwards kind of thing, right? Is that something that was working before now isn't working because you've injected bugs into something that was previously mature, but you've laid the foundation for being able to do something that you were being able to take a new approach to solving some aspect, some problem that you just weren't making progress on in the old approach. And I feel like they did that in a very significant way here because they previously kind of had separate perception systems for moving objects and static objects. And they've stopped doing that. They've unified the thing, which that's a big simplification. It's a conceptual simplification and unification of the perceptions of the system. It eliminates optimization they had before because static objects, you don't have to think about as much because you just assume they're not going to move. So in a sense, it's an optimization to break your system into 2 pieces and say, I only need to check on these once in a while because they're not going to move. But there are these other things I need to pay more attention to. So I'm going to spend more code and do more sophisticated processing on those kinds of things. But then, whether you put things in the right category, can really bite you. You can have all these problems with it. And I'd always really worried about the fact that they had these 2 split and they're getting rid of the split. They're just like, we're not doing that anymore. Everything's a thing and we're putting it all in one bucket. And we don't have we're not going to have the complexity that and the weird problems that will manifest from getting things in the wrong categories or not being able to recognize things. Like if you can't recognize something, what category does it go in, right? Is a big problem in that situation. Yeah. And they've gotten away from that. And so that's the kind of thing where, the potential for the big step backwards, where all kinds of things that worked before are now going to manifest new problems that people with experience with the system haven't seen before. But the flip side is there's all these problems that they're probably having or that they would have in the future that they're just not going to have because they're taking a conceptually much more straightforward approach to dealing with it.
So do you think that's one of the reasons why they're doing 10.69 just for limited and then 10.69.1 for more and then more wider release for the next release?
It's big changes. These are big changes to the system. So yeah, I think, the risk that there's some really horrible bug hiding in there that they just haven't got enough miles to discover yet is too high for them to just give it to a ton of people and turn it loose. You definitely, going to want to, baby step this thing out into the world.
Yeah. So with Ashok's presentation, so he spoke, I think it was last week, and there's a YouTube video on that. I'll try to link it in the video description if I remember. But yeah, it was a great talk. Could you kind of share kind of the layperson overview on what's significant about his talk? What can we learn about what Tesla is doing right now in terms of their neural networks and their approach, to self-driving? Where are they at, and kind of what's the bigger picture here?
Yeah, so it's another recruiting kind of event. So Tesla's not going there doing the big reveal and showing us everything that they're doing. They're dribbling out some technical details that are going to be interesting to the audience whose interests they want to pique. And we get to sit on the sidelines, not being the audience that they're trying to recruit, and sort of get to see some stuff that they haven't shown before. And there were, from a technical perspective, there were a lot of really sort of interesting things to me in the talk. The place I was going with the anecdote before I ran on was he has this phrase about geometry is greater than ontology, and which is so. Ontology is putting stuff in categories, right? Like making sense of the world by by recognizing things and putting them in boxes. And that is a pretty good way of describing what a lot of self-drive, a lot of the underlying tech, one of the things that neural networks are good at is I have my dog cat, example that I've talked about a bunch of times. Is this a picture of a dog, a picture of a cat? That's a classification thing. And a ton of the underlying core tech, classification was one of the first problems people tackled with networks. When they started applying neural networks to cars, classification was a natural place to go. It was something that was kind of understood how the technology worked in that in that way. And so they did a lot of classification, right? Is this a stop sign? Is this stoplight red or green? Is this a curb? Is this a curb? Is this a curb? Is this drivable space or not drivable space? Those are all classification decisions, right? The perception of the world was heavily dominated by classifying objects and delineating their boundaries, and then trying to make decisions that way. Mm-hmm. That breaks in ways. It's very useful in lots of ways. Like knowing something is, say, a pedestrian as opposed to a light pole. They're both just things in space. But when you want to predict what things are going to do, recognizing what they are is super useful. So you don't want to get rid of classification. That's really important. But there are aspects of this problem of being in the world and maneuvering in the world where you just need geometry. You need to know, what space is occupied by something and what space isn't occupied by stuff. That's the occupancy map, right? Mm. And they're shifting a significant amount of work into determining this occupancy thing. And so Ashok spent some time talking about giving some examples of how they're doing occupancy, how they're building this 3D map of the world around them to understand what's empty space and what has stuff, what points have stuff in it. And there are things that you can get out of that really help you sort of understand the situation and perception in a basic way. He did detail, and not enough detail, not as much as I would like, but he talked some about how they're doing occupancy and how it affects what they're doing. But to me, from a lay audience standpoint, the big takeaway is they're putting a lot more effort into understanding the geometry of a system and using that to their advantage. And they're relying less on their ability to accurately classify all the different things that they see.
Interesting.
So that's the broadest takeaway that
Got it. Okay, so let me clarify these terminologies like occupancy network, let's say vector space. We talked about bird's eye view in the past. So for example, we're all talking about, let's say, 3D space around us, right? And would you say that's like vector space is a close kind of definition to that? And then occupancy network is more defining how you view that 3D space. And then bird's eye view is just one aspect of the angle of that, what you're looking at in terms of how you're viewing that 3D space?
We don't know exactly how Tesla defines the terms internally, so we guess a little bit on some of this stuff. For instance, vector space wasn't something that they ever perfectly defined. But in the way that they used it, we take vector space to be sort of a 3D representation of the objects in the environment. And now they've kind of moved away from vector space, at least in Ashok's talk, they moved away from vector space as part of the terminology. And they're now talking about occupancy. He used the term occupancy network a lot. Yeah. The difference between an occupancy network and an occupancy map, by the way, is occupancy network is the neural network that produces the occupancy map. Internally, they're building an occupancy network that predicts occupancy. And when I've been talking about this, I keep using the term occupancy map, which is it's the data structure that comes out of an occupancy network. It's easier to think about, I think. Like this, we have this network because we want this kind of output. And here's why we want this kind of output. So I keep talking about the map, which is the data that comes out of it. So when the map itself is like the voxel-based representation of the space.
Got it. So the occupancy map is basically the 3D space mapped out of all the different objects and what they're doing in that 3D space.
Yeah.
And that's produced by an occupancy network, which is basically a neural network that's analyzing all the data feeds.
It's just one slight difference there, right? So instead of saying, there is a car and it is here, right? What an occupancy map does is it takes a space around you and it breaks it up into blocks. And I don't know what the current grid size is, but it was 1 foot before. Approximately.
Got it.
So imagine taking all the space around you and making it into a 3D 1 foot grid. And then inside each one of those blocks, you have a label for what stuff is in that box, right? So essentially you break all the space around the car down into this 1 foot grid. And then you say, is this just empty air? Is this a curb? Is this a tree? Is this a backhoe? Is this the shovel on the back of a backhoe hanging into, whatever it is? You've got a label for all of these things in 3D space over the space you care about, going up 10 feet or 20 feet and going out maybe 100 feet or 200 feet in every direction, right? You just have a box that the car is centered in, and you're labeling everything inside that space. And once you've got those, the neural network produces all those labels. Now, and then downstream neural networks can consume those labels. They take that as input to make planning decisions about what they're going to do, or control decisions. They could do that too. And then it's also a representation that human beings understand pretty well. So for instance, if I have an occupancy map like that, I can render it. Like I can make a little 3D model of it that a human being can look at and say, does this make sense? And you can use that to debug the map, to understand stuff. And they actually do that with with this trick. So there's a thing called a NERF, neural rendering field. That was another piece of technology that came up in the thing. And they can use a NERF to basically take the output and turn it into like a 3D picture that a human can look at. And you can tell if the neural network's doing its job or not, for one thing, right? So that's one of the reasons the structure is useful, is because people can understand it. It's not a total black box.
Sure. You could basically label it later, or for errors, you can get the errors and easily label it as well.
Yeah, and labeling. I mean, so you can do your auto labeler. You take your clip from the car and you dump it into the auto labeler, and the auto labeler generates all the labels and stuff for all the objects that you wanted in the 2D frame for classification and that kind of stuff. But the auto labeler is also making the voxel labels for the 3D space. And then if you want a human to be able to look at that, to tell if the auto labeler is doing its job or to make corrections or whatnot, you have to convert it into something a human being can understand.
Yeah.
And so a NERF is basically a way of taking this voxel output, turning it into a 3D, drivable animated scene. And then a human can say, oh, that's a pedestrian, and this is a fire plug, and this is a mailbox. You can label those things once you've rendered in a format a human can understand.
Got it. So with these occupancy networks and occupancy maps, so we've got this 3D space that's mapped out, let's say one by one grid of the whole space. So where does predictions come in? Like, for example, let's say a car is moving this way and a different car is moving this way, and if you drive at a certain place and you're going to get hit by that car, like how do they bring that into
the occupancy map? This is all pre-prediction.
Okay.
Right. So you got a stack of neural networks. And in the beginning, we've talked about this a bunch of times. You've got perception, which is understanding the current situation. To the best of your ability, you use the sensors, you take the data in, and you build a usable representation of the situation that you're in. Then other parts of the system take that representation and they do planning. What should I do? And then after that, there's another part of the system, which is not neural networks, or mostly not. It's mostly not neural networks right now, which actually takes that plan and then turns the steering wheel, hits the brakes, and that kind of stuff, right? So some of the planning is done as neural networks, and some of it is done in not neural networks. Like in Ashok's talk, they talked about this implicit collision network thing that they were doing, and that which is let's transition to that topic for a minute, because it's a nice sort of example of what's going on here. That is explicitly a planning function. So the thing is, in the part of the talk where Ashok was talking about their, having systems that assist drivers in avoiding collisions. So when you misapply a pedal, or maybe you're doing something wrong, or maybe you've passed out, and the car is going to intervene in order to go. So part of and of course, this stuff would all apply when the car is driving an autopilot. Also, these tools are all available, but being able to make a plan. Like, okay, here's the situation. I'm going, 20 miles an hour. This is the shape of the road, and here's a wall. Am I going to hit the wall, right? And if there's a risk I'm going to hit the wall, what should I do to avoid hitting the wall? Should I brake? Should I turn right? And you have to take everything in the So that's a planning function. So the implicit collision network is a clever way of generating a neural network output that a regular heuristic algorithm can use to search through the space of possible future actions to find good ones, and that becomes the plan, right? So that's a neural network producing an output, which is it's a perception, but it's a perception that is specifically formulated in a way that it's easy to write a program to search through the possibilities. But because building the neural network so that the neural network searches through the possibilities can be complicated. If you have a set of choices, like if you're going to drive down a road, if you're avoiding obstacles, you have to say turn the wheel left, decelerate, turn the wheel right. You have to plan forward in time, and what you do right now might depend a lot on what it means for what your options are 4 or 5 or 6 steps down the road. So to do that, we don't usually have a neural network do what's called the rollout, where it takes a step and then evaluates and takes a step and does evaluate. Instead, what we want is we want a neural network to produce a sort of an evaluation function that another program can basically use to step through the possibilities. And in a car, you've got to do this quickly. Like you want to evaluate this in a few milliseconds. So the neural network output has to be formulated in a way where it's very easy for a conventional program to quickly roll through, to search the tree of possibilities to find a good outcome, or to find an optimal outcome relatively quickly. And this implicit collision network is a way of doing that. It's you take the situation as the car perceives it, and then you render it in a form. Because I think if you look at the talk, the explanation is like, well, why do they have this map and which direction the car is facing changes collision probabilities going with a 10-second horizon or 20-second horizon? It seems kind of not the most obvious way to describe this thing. And the reason they do it is because an algorithm can quickly use that map to search all the possibilities to determine an optimal plan. So this is kind of how neural networks contribute to your ability to plan. They can take the perception and put it in a format where a regular program can quickly check out all the possibilities and decide what the best one is.
Got it. So to clarify all this, so the cameras, the neural nets are taking the data from the cameras and basically creating a 3D space, let's say occupancy map. And then from that, the neural nets are also evaluating that map, let's say for, collision, I guess implicit collision network, perhaps maybe like, figuring out what's the risks involved in different, paths. And then the planning takes all that output and then evaluates it mostly through heuristics, I'm guessing, to create the optimal plan for it, right? So AlphaGo, it had a neural network
that would basically tell you, is this position good or bad? And of all the moves you could take on the board, which one at this point in the game is a good move to take, right? Like it would just, of all 300 moves or whatever that you could do, it would rank them from best to worst, right? But the thing is, you can't play a game just always picking the best move, because sometimes subtle things happen 2, 3, 4 moves down the road. I mean, if your evaluation function is good enough that it can say, that it can look way, it can guess what will happen way down the road if you do a particular thing. So in the first version of AlphaGo, what they did was they did Monte Carlo rollouts. The time horizon that the neural network could see forward to understand the implications wasn't super far. It was 2 or 3 or 4 stones, 2 or 3, 4 moves, right? But what they could do is, because they had this neural network that would just basically say, these are your best 10 options in this position. And then you could say, well, for each one of those, what would be my next best 10 options? So you go from, 10 to 100 to 1,000, it multiplies by 10 at each step, but if you search this whole tree. But what you get from that is you're using your evaluation function to kind of search a possible tree of decisions that you're going to make. So in a sense, this is doing that's called a rollout, when you basically use a network to make a decision. And then you say, well, what would I do next? And what would those are, you're rolling out a sequence of possibilities. So it's writing code to do rollouts, especially, is an easy way to make your planning horizon farther. Like your neural network, if you just train it from the ground up and you say, which way should I turn the wheel, right? It typically, at any given level of capability, you'll have a certain amount of time forward that it can easily predict. And as it gets better, it'll be able to predict forward much further. It'll take more things into account, and more second order effects and third order effects and what happens next and so on, and be able to produce a good decision. But barring that, when you're at a certain level of capability, what you'd like to be able to do to just get the neural network you have is run it multiple times on subsequent time steps. That's a rollout. So the planning function, to the extent that your neural network isn't godlike in its perception and able to always give you the best answer, one way to just make it better is to have it guess and then pause it. Okay, and then what would you do after that, as a way of just searching through the tree of possible futures that you might want to consider. But if you're going to do that heuristically, it involves running the neural network many, many times for each decision that you make. So you need the neural network that produces that output to be pretty quick, because you're going to have to run it a bunch of times. And you need the algorithm that evaluates that and chooses the next possibility to also be very simple, because you have to run it many times.
Got it.
So the cleverness in this implicit collision algorithm is it strikes a nice balance there. They produce a relatively simple neural network that can be run many times, and they also produce it produces an output that a heuristic can easily evaluate to make decisions about which future states do I want to consider.
Got it. So is there any terminology of what this implicit collision network outputs? Like with the occupancy network, it outputs an occupancy map. Is there anything similar? Yeah. Tesla's making up words for a lot of these things because they're inventing the stuff. Yeah. And so they probably have internal wording for it. There may be other people who've done this. Frequently, it's been the case when I go look at stuff, Tesla has come up with it. Somebody else had the idea, and they saw it and they adapted it or whatever the deal is. I don't know where this idea comes from, so I don't know what the other terminology would be for it. Got it. So back a while ago, we were positing that version 11 would be like a unification of, let's say, the highway networks, the local driving networks, and the parking lot networks all together. Is Tesla getting close to that? Do you think there's part of this unification already happening with the current builds?
It's possible they're doing it. They're not talking about it. And I haven't looked at the code myself in quite a while. My guess is they set that aside and they're focusing on other things. I think that my guess would be that some of these capabilities they expected to get without having to do a lot of work. And so when they were looking down the road, they were like, the next thing will be unifying all the networks, right? But they bumped up against some obstacles that they just weren't making progress on. And they've had to go back, make some changes. They finally breaking through those obstacles. But they basically stopped worrying about trying to because unifying the stacks, it gets you some things that eventually they need to have. but you don't care about those things until you've got the surface, until you've got your city street driving, basically, where like I feel like the stack thing, it basically gets you not hatch modes when you get on and off a freeway to switch into autopilot. It gets you better perception on autopilot. FSD is definitely better than autopilot as long as you operate inside a velocity that it's capable of. But my sense is that FSD has got some limitations in it where you can't safely use it at high speeds. And so that's why they're not using it on highways right now. Plus, they have autopilot and it works pretty well. So they might as well just keep using that. So unifying those would be nice. It would simplify the system. It would reduce, the overhead that they have. It's great, but it's not a priority right now because they have a system that works well enough on the highway. So they're just not doing it. And then the other thing is like parking lots. Parking lots, like the system's not good at parking lots right now, in my opinion. And unifying the stack is an opportunity to like get significantly better performance in parking lots, but it's a trade-off. It adds a significant amount of complexity, and it might have negative consequences for your just driving on surface streets.
Got it.
So, that's not something that you want to take. That's probably not something that you want to do. Pretty happy with your surface streets. And so like my general sense is the surface streets thing took longer. They had some fundamental problems. They've gone back. They've reevaluated some stuff, including moving to geometry because they've discovered that just lots of classification with simpler spatial stuff wasn't good enough. So they re-architected that. And maybe it'll be good enough now after they roll this thing out. And like if they feel like they've made enough progress on city streets, then maybe they go back to doing the stack unification.
Yeah, interesting.
Or maybe they did it and they just didn't tell us. I think that's unlikely.
Yeah.
And because it's still not good in parking lots, at least as it. We'll see. It'll be really fun. When I get 1069, I'll try navigating to and from parking lots. And like if it's significantly better at making the transition from surface streets to parking lots and maneuvering in parking lots, then maybe I'll feel like they made progress on unifying the stack. Yeah.
Makes sense. So I wanted to dive into a bit with the 10.69 release notes. It's always helpful to get your kind of take on this. Right before we started recording, you were just reviewing them quickly and you're like, oh, everything's pretty straightforward. And I was commenting like, for most people, no, it's like the terminology is so foreign, Exactly. And so I think what I'd love for you to do is maybe go through a few of these and just in layman's term, just like explain kind of fundamentally what's going on, like what are the key improvements in 10.69 that at least Tesla highlights. I'm sure there's a bunch more, improvements under the hood. But the first one, it says, added a new deep lane guidance module to the vector lanes neural network, which fuses features extracted from the video streams with course map data, for example, lane counts and lane connectivities. This architecture achieves a 44% lower error rate on lane topology compared to the previous model, enabling smoother control before lanes, and their connectivities become visually apparent. This provides a way to make every autopilot drive as good as someone driving their own commute, yet in a sufficiently general way that adapts for road changes. All right, so translation.
So that last part seems like a subjective evaluation that I will have to withhold. Yeah, so we've been talking about how they've been adding GPTs, right, transformers and other sort of feature evaluators to make representations that are easier to make decisions on. And it sounds like, so they had this vector lanes neural network that they added in, was it 10.11 or 10.12? I can't remember. But anyway, they introduced that. And then the intersection behavior improved significantly because previously they had been using the giant bag of points and then having an algorithm that ran through it to try to understand the lane. When you come up to an intersection and you're going to make a decision about going or stopping or turning or not turning, you need to understand what's the intersection. And what that means is like, how many lanes come in, how many lanes go out, what lanes can connect to other lanes? Like, can this one turn right? Can that one turn left? Most intersections that you come to as a human being, you look at that and you just know this one goes straight. And sometimes because there are markings. And sometimes because it's just obvious from the intersection. The shape of the intersection tells you. So in the past, prior to having the neural network thing, they were doing that with a program, right? Essentially, that was just basically taking a little 2D map, where all the stripes were, and saying, with a human written program, this lane must connect to that one, and this one must be a right turn lane, and that kind of stuff. And what they switched to is they took that and they stuffed it in a neural network, and the neural network came out and it just produced a set of continuity trajectories. Like this is a possible trajectory, that is one, and so on. So they let the neural network figure that out. And in edge cases, if you have a weird intersection, and if you look at FSD videos, people delight in going out and finding weird intersections, right? Those are really tough to write for a human to anticipate every possible weird thing that could happen and what you should do. Neural networks are better at taking some weird thing that kind of looks like something that but is different in one important way, and understanding what the connectivity is. So they added that a couple versions back. And this is basically, we added to it because it wasn't good enough, essentially. They added another module on top of the thing to essentially deepen the thing's understanding and its ability to predict this connectivity in edge cases.
Got it. So they're talking about coarse map data, so like lane counts and lane connectivity. So what I'm taking this to be is, so they have this vector lanes neural network, right, that determines all the lanes and their trajectories. And now they've added to that kind of like what the lanes are going to look like further out based upon some basic map data of like how many lanes a street might have, or, where the lanes head. Let's say 2 lanes merge into one or something. So they're predicting these lanes further out, which gives them more accuracy. Is that kind of what they're doing?
I'm taking it a slightly different way.
Okay.
And it's vague. So, this is not super specific. The thing I'm taking is that the previous version of the neural network, it didn't take map data in. So like the navigation map, one of the things the navigation maps will have, ideally it will be accurate, but it isn't always accurate. It is like this road is 2 lanes going this way and 2 lanes going this way. Or at an intersection, they'll have data that says, there's 3 lanes at these intersections here. And the map data might say there's a right turn lane and a left turn lane, or whatever the deal is. So the neural network previously was just like taking the cameras in and basically saying, here's what I see, and then making its decision based on that. And now what they've done is they've added a feature where it can take the navigation data and it can consider that in its solution for that thing. So like if the neural network is like, is that 2 lanes or 3 lanes, and it's not quite sure, but it's got this coarse map data that's just basically saying, this intersection should be 3. It's like, I'm going to err on 3 because that was what the map says, and that'll improve that accuracy.
Got it. So it's not just predicting like further out; it's predicting right now what the lanes are around it. Got it.
Now, of course, a side effect of this is that you can predict farther out, because of course one of the things that happens with further out is that the closer you are, the better you can see something, the more accurate the neural network is going to be. Like, it might look at a road and say, this is 2 lanes, 2 lanes, 2 lanes. And the farther it gets and the less well it can see, it's like 2, 3, 2, 1 might be less. And if the map says 2, then the neural network might decide, okay, I'm going to say 2 because that's what the map says.
Yeah. So before, were they not adding this coarse map data to their vector lanes neural network, you think?
Well, the way this is worded implies that they weren't, because they added it.
Yeah. Yeah, it seems like, the vector lanes neural network is a big upgrade, feels like, to get more accurate lane predictions, lanes. And it seems like adding coarse map data seems like it could be a big improvement. They're saying that it achieves a 44% lower error rate on lane topology compared to previous model. that's a big improvement. Wow.
But now, remember, a 44% improvement it might have been that it was, 99.0% good, so it had 1% error. And a 44% improvement is now it's 99.44%
Got it.
good. So the error rate has gone from, whatever it was before to, 56% of what it was. So it's essentially a doubling in a reduction by a factor of about 2 in your error. But the thing is, once again, these are edge cases, because it's already pretty good at getting most of the intersections most of the time. And you can imagine how, when you first run the thing out, let's just put the neural network in, see how the neural network does based on the cameras. You run it in the world for a while and you say, okay, here's where we're having problems. And then you look at the thing and you say, well, you know what? The map data is mostly right in those situations. So how about we have the neural network consider what the map says when it is making decisions about this stuff. And so they add a feature to the neural network where it can take that map data and take it as an input as one of the things it does. Now, of course, one of the problems with map data is if you rely too heavily on map data, you can remember, because maps have errors, and sometimes the errors are egregiously bad. And so if you assume the map is right, occasionally you will get in a really tough spot.
Got it. Interesting.
So you can't totally trust it. You want the neural network to look at the map, look at what it sees, and make a value judgment. It's like the map says there's 10 lanes and I only see 2. Right? That might be a typo.
Yeah. Yeah. I mean, I guess that's one of the benefits of having a vision kind of, focus approach is you could rely on vision more than just, let's say HD maps or, what.
And that's kind of what you want.
Yeah.
I mean, that's what a human being does, right? Yeah. You trust your perception.
Mm-hmm.
But I mean, in the case of a human, the comparison is probably what you remember. Like imagine that you're driving someplace you've driven before, but you haven't driven recently. So you have a general memory that, after I come over this hill, I'm going to want to turn right. And I want to be in the right-hand lane because that's the only lane that can turn right. Like that's your memory of it. And so you might use that, right? But because it's a memory, if it's wrong, or if you come over the hill and there's a cone in that lane, then you have to change your plan. And you want the vision system to look and say, there's a truck parked in that lane. What's plan B, right?
Exactly.
You want the vision to take priority because it's got a concrete understanding of the world. But you in situations where your horizon extends out too far, or there's some ambiguity in what you see, having the map to like split, to essentially do the tiebreaker for you it can. And this is kind of what it's doing. If they're getting a 44% improvement, then half the time the map data is resolving what was a problem for them before, right?
Yeah, definitely. I mean, it brings up also the big challenge with multi-sensor fusion. It's like if you're relying on LiDAR and HD maps and vision and radar and all these things, it's like how do you give priority? It's like, I mean, it's just more confusing than if you're doing a vision, focus approach, and course map data is just there to help you in case,
Yeah, sensor fusion is just like one category of input fusion, where you have inputs and they all have some amount of error and you have to bring them all together. Occasionally you're making decisions about, in this situation, how reliable is this data versus that one? Or given what I see, should I trust that? It can get really subtle.
Yeah. The second release note says for 10.69 says improved overall driving smoothness without sacrificing latency through better modeling of system and actuation latency and trajectory planning. Trajectory Planner now independently accounts for latency from steering commands to actual steering actuation as well as acceleration and brake commands to actuation. This results in a trajectory that is a more accurate model of how the vehicle will drive. This allows better downstream controller tracking and smoothness while also allowing a more accurate response during harsh maneuvers.
Yeah. So this sounds like previously they had a very simple model of the car dynamics. So you want to have a model of the car dynamics. When you convert your plan into a set of actions and you have an envelope, like you don't want too much acceleration or too much turning force, you don't want any jerk, and you're turning into a lane that's over there, and you want your car to hit the center of the lane exactly, not to be too far left or too far right or whatnot. You need to have a model of the consequences of what you do, like how that happens going forward. And in the beginning, you can start with a really simple model. Simple models are better because they're less likely to have bugs and they're less likely to have weird second order effects and stuff like that create other problems for you. But once you're pretty, at some point you get to where the limiting factor in being able to hit the center of the lane when you do your right turn or your left turn is, my model of the car assumes it rotates about its center as opposed to like the front wheels turn and the back ones do, and it's this long. So upping that model, and in this case, they're not talking about a geometry thing. They're talking about latency. Like when you start to turn the steering wheel, right, how long does it take before I've got the wheel all the way to the position that I'm going to complete? Because you can imagine the planner says, okay, I'm going to turn right, boop, and in the model, the wheels instantly go to 45 degrees. And of course, in reality, that's not what happens, right? The wheels slowly turn over. And if you take that into account when you make your turns, you make smoother, more accurate turns. So,
all right. That makes sense. Next release note, improved unprotected left turns with more appropriate speed profile when approaching and exiting median crossover regions in the presence of high-speed cross traffic. quote unquote Chuck Cook style unprotected left turns. This was done by allowing optimizable initial jerk to mimic the harsh pedal pressed by a human when required to go in front of high-speed objects. Also improved lateral profile approaching such safety regions to allow for better pose that aligns well for exiting the region. Finally, improved interaction with objects that are entering or waiting inside the median crossover region with better modeling of their future intent.
Yeah, so that's a ton of stuff.
Yeah.
So that's a laundry list of things that they tackled in order to make the Chuck Cook style left turn work. It's a ton of stuff. But so what parts of this?
So I mean, so they're basically saying like to get into the median, right? They improved basically probably modeling of how to get in quick, the right speed, how to get in, and then. But what does this mean? This was done by allowing optimizable initial jerk to mimic the harsh pedal pressed by a human. Yeah. So does that mean they're just making the speed just more comfortable, like a human, like would go into that?
So jerk
median?
is the rate of change of acceleration. So like there's position and the first derivative is velocity. It's a rate of change of position. The rate of change of velocity is acceleration. Jerk is the technical name for the rate of change of acceleration. So that's like how fast you push the gas pedal down, not where is the gas pedal, but how fast do you push it down. So essentially they modeled and that's something people are really sensitive to. Like a big component of comfort for human beings in longitudinal control of a vehicle, forward and backwards control, is not what level the brake is at, but how fast did you get the brake to that point, or not where the accelerator, how fast did you get that? So they're now essentially, this is similar to the piece we were talking about before, where you're not assuming that the wheels instantly turn to whatever the position is when you're doing your turn. You assume that they gradually get there. And they're similarly, they're not modeling that the accelerator went from 0 to 0.2 instantly, but that it slowly got there, or that it got there with some movement profile. And once again, that affects, where that affect, like if you're trying to predict, like where will the car go if I do this set of actions and how will it feel to the occupants? If your accelerator model or your brake model is crude enough, then that limits your, what you can do within a certain comfort profile. So now in a Chuck Cook style turn, you want to be able to get aggressive, but you don't want to be slamming people around the inside of the car. So you have to get more refined in that, like, what does aggressive mean exactly? Like what sets of controls can I do that will get me moving quick, but which won't, make my, leave bruises on the occupants.
Got it. That makes sense. And then basically also improving the position, I guess, that gets into the median and interacting with objects that are entering or waiting to enter. Makes general sense.
So that's really complicated, right? I mean, medians, they're different sizes.
Yeah.
Some are only going to fit one car. Some will fit two, depending on whether a median is like a little to the left, or the gap in the median is a little to the left or a little to the right. You might imagine that cars coming in, it might, because sometimes when you turn through a median, you turn to the left of oncoming cars. And, other median geometries, you turn past the car, right? You go to the right of the oncoming car and you turn around each other when you enter. Yeah. And so understanding that from the shape of the median and, is a little bit subtle. But if it's a Chuck Cook style stop, because people use that median not just to turn left from Chuck Street onto the thing, but to turn onto Chuck Street. And some of them are doing U-turns. So you have to look at the thing and sort of infer that all these things might be happening. And when you see a car coming or entering, like predicting, like what is he doing? What should I expect him to do? And what is he expecting me to do? That's all part of modeling this dance, which you have to get right. And you have to get it right quickly, because you're playing in traffic. You're not moving very fast and cars are coming at you quickly.
Got it. Makes sense. The next piece note says added control for arbitrary low speed moving volumes from Occupancy Network. This also enables finer control for more precise object shapes that cannot be easily represented by a cuboid primitive. This required predicting velocity at every 3D voxel. We may now control for slow moving UFOs. Yeah.
So this, we talked about how they were moving away from needing to recognize things really well. So one of the things about a about classification is. The fundamental classification sort of delimiter that Tesla uses is a cuboid. It's a three-dimensional volume, the minimum three-dimensional volume, which contains all of something. Like if it's a truck, what's the smallest cube I can draw around that thing that where all of the truck is inside the cube. And then the car treats that as the boundary that it needs to stay out of. But when you get complicated things, especially in tight situations, like imagine that you have, like a utility truck with like one of those cherry pickers hanging off the side of it, parked on a narrow residential road with some cones, and you have to move around it. Well, you want to know that you can, if the cherry picker's 20 feet up, right, and it's off to the side, you want to know you can drive under it. If you draw a cuboid around that thing that includes it, it seems like it's occluding the whole road. So you need this kind of more subtle understanding of how singular objects decompose into occupied volumes of space so that you can maneuver around them in tight situations. And so by moving away from just recognizing and classifying things and treating them as like these things, especially in a situation where on a certain level, everything the car sees is a cube, right? That becomes a big constraint in some situations. And they're moving away from that. And that also gets you a thing where if you start focusing on what's occupied, you can deal with things that you don't recognize very well. Like if you got a pile of dirt in the road, or you got a pile of something, garbage, or, you have a human being collapse on the road, but you don't recognize it as a human because they have some garbage laying on them or whatever. You can start to deal with just arbitrary things in the world that you've never encountered before, but which you need to understand the shape of them so that you can around them. And they apply velocity to it too. So if you see some weird thing moving, like a tumbleweed, right? So I don't know if they have a tumbleweed classifier. Yeah. Maybe they do, but it's this arbitrary thing that's moving across the road. Like it's not really a static object. It's kind of a static object. It happens to be blowing, but it's not moving of its own will, right? And so how do you deal with the fact that there's this thing moving across the road slowly that you need to be aware of? And so geometry is a way of just dealing with all of that stuff as a single category, right? Even if you don't recognize it, even if it's moving but not moving like a highway, like, a road user, right? You can still deal with it.
Interesting. So what does it mean by, it says this required predicting velocity at every 3D voxel?
Yeah. So when you see the tumbleweed moving across the road, the way the occupancy network, recognizes it, it has some label for, I don't know, vegetative matter or something like that. The labels for the individual voxels, they're not decided by a person. A neural network figures out for, I have, 128 bytes to describe what is in this voxel, and I'm going to allocate them this way. And, there will be some representation for that will map onto what a tumbleweed is moving across the road, that will capture its properties and that kind of stuff, the rough shape of it and what part of the tumbleweed that you're looking at. So you have a tumbleweed moving through a voxel. One of the things you want to understand is of the stuff that's in this voxel, what of it is moving and in what direction is it moving? So if you're going to deal, your choices are, you either represent velocity for every voxel, like the stuff in this voxel is moving that way at 1 meter per second, or you don't do that. If you don't do that, then all the decisions that you're going to make based on that, they have to assume that everything is completely static. So now you can't deal with the tumbleweed effectively, like if you don't want to hit it, or if you don't want to have to recognize it as an object. So having velocity for these arbitrary geometry things is useful. Like it enables you to make a lot of decisions well that you otherwise wouldn't be able to make well, but it requires you to not only evaluate that there is something here, but that it's moving, such that like 1 second from now, it'll be in this position, and 2 seconds or 100 milliseconds forward or whatever. So that means they have to label every single voxel with velocity.
Got it. And then we may now control for slow moving UFOs. I mean, what's a UFO?
A tumbleweed.
Okay. Unidentified.
Something
is it
you don't recognize?
Is it? It's not flying object. Is it? What's a Is it just unidentified object, or a moving
Yeah,
object
maybe.
or something.
I don't know
Okay.
what their TLA means in this situation,
Okay.
but I guess just UFO.
Got it. Okay. Next release, an upgraded occupancy network to use video instead of images from single time step. Okay. This temporal context allows the network to be robust to temporary occlusions and enables prediction of occupancy flow. Also, improved ground truth with semantics-driven outlier rejection, hard example mining, and increase the data set by 2.4 times. Yeah, what does this mean? Upgraded occupancy network to use video instead of images from single time step. What is this single time step?
Sorry. The way to read this is upgraded occupancy network to use video instead of images from single time step.
Oh, okay, got it.
Right. So instead of training
okay.
the occupancy map based on single slices of time,
Yeah.
and this is part and parcel of having velocity for the occupancy map. Obviously, if you're going to predict velocity, you have to look at how it's evolving over time. If you're going to look at how it's evolving over time, you need to take into account multiple moments in time separated, right? And so they're using video. Video is multiple images equally spaced.
This seems like the most important update. I mean, why isn't this like number one? If you're gonna, move from images to video,
it kind of feels like they're saying the same thing. I don't know.
Okay, from the past, it's inferred maybe from the previous. Stuff.
I don't know. It probably, if I thought about it, there would be some way of understanding this as distinct from other things that they're saying. But it does seem kind of implied by the other stuff that they're doing. I mean, would you agree that this is like generally taking a step back, one of the big things that they're doing, with this release, not just with this release, probably over some period of time, which is moving away from, just from single time step, into video and into this occupancy network to geometry.
Yeah, exactly.
Or they're not giving up on ontology. They're just relying less on it, and they're having better geometry, and they're using it better.
Yeah. I mean, this just seems like it's like, this seems to be one of the big kind of, I guess, I don't say milestones, but big, I guess, movements or improvements, for FSD, in this season, which is this occupancy network, video, accounting for occlusions, allowing for predictions, just kind of like a better, more accurate perception, right, engine. Yeah, definitely. Interesting. All right.
The geometry thing, I'm super happy to see them, moving more to because trying to rely entirely on classification or rely too heavily on classification, gets tricky. Like classification, the BEV thing is kind of it's kind of this middle ground between geometry and classification. I mean, you're getting 2 3D stuff when you go to BEV, when you use bird's eye view networks. But you're kind of carrying the baggage of classification along with you when you go into that. You're still basically saying, looking from the top, there's a car at this position, blah, 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 blah. But the car's still a cuboid, right? So if you imagine that you have a truck driving through and it's got some weird trailer hanging off the back of a boat or something, right? It's like you can't, it's hard to do a recognition that's going to be able to deal with every single kind of thing that might be on a trailer and every kind of trailer, because there are all kinds of weird trailers in the world. And so geometry kind of deals reasonably in those situations where your classifier is just like bumping up against a wall.
Got it. So, I mean, when you talk about geometry versus just, let's say, ontology or classifying, with geometry, you could break down these objects, I guess, more specifically, and kind of, it's a more granular approach, basically. Than just
you see every object becomes
ontology.
Stuff in space. In addition to being like a human being is stuff in space. But one of the cool things about this is that stuff in space that doesn't have a label is still stuff in space. Whereas with a classifier, you kind of have this problem where stuff that you don't have a label for kind of doesn't exist, right? And so that creates these holes in the way that that you can address things effectively.
Yeah, that makes sense. I mean, would that also help? Like, I remember this one situation. This was back, I think, last summer when we were driving FSD in my car. We went into this area with a gated community, and there was this gate, and it felt like the car was just gonna drive through the gate. Yeah. It was a small gate. This is like a line thing, and I stopped. I stopped. I'm like, whoa, this is crazy. I mean, is that one example where
Yeah.
At
No,
that
that's a
time
perfect example.
it didn't classify that maybe at that time.
Yeah, well, it saw
But
that thing and it's like, that doesn't look like a gate.
yeah, exactly. So
There's
it's
nothing
nothing. There's
there,
nothing.
right?
But geometry, at least you would say, hey, there's something there that's
But so the
static.
geometry will
Yeah.
say, it may not be a gate, it's still stuff.
Yeah. Got it. Yeah, it's important stuff, man. All right, let's do our last release note. There are more release notes here, but I think for time's sake, upgraded to a new two-stage architecture to produce object kinematics, for example, velocity, acceleration, yaw rate, where network compute is allocated O objects instead of O space. This improved velocity estimates for far-away crossing vehicles by 20% while using 1/10 of the compute.
Yeah. So that O notation is it's a way of describing how an approach to solving a problem scales as the number of things you deal with increases. So what they did was they essentially went to a network, and processing approach to dealing with objects where it doesn't like if your processing goes as O space, then if you want to look twice as far down the road, it takes twice as much compute. And if you want to look 4 times down the road, it takes 4 times as much compute. In other words, but it goes as it's not just linear stuff. It goes as space, right? So, if you want to evaluate everything that's 20 feet up and 100 feet down and 100 feet on both sides, that takes 1/8 as much processing as if you want to go twice as far in each one of those directions, right?
Sure.
But the thing is, there are a lot of things in the world where you don't want to waste compute on all these things. Like, for instance, if the thing you're looking at right now, if the aspect of reality that you're trying to extract right at this moment is about objects, then you don't want your compute to scale with space, because you could have this huge volume of space with no objects or one object in it. And if you essentially want to, double the linear dimension that you can see distance wise in each direction, you got to add 8 times the compute and 8 times the memory, and it just becomes very resource intensive.
Got it.
If what you care about is objects, what you want is something that scales with the number of objects. So if you have 4 pedestrians or 8 pedestrians or 12 pedestrians, it scales with that and not with, and this is an important thing for being able to get FSD to where you can use it on the highway, right? Because on the highway, you're frequently in a sparse situation, but you have big distances involved because you're moving fast. You need to be able to look pretty far away. And I think I'd actually brought this up, this whole scaling with volume of space as being a limiter for FSD. Like you can only make the BEV map so big because the compute grows as the map gets bigger. So if there are aspects of the BEV map, like maybe you can't fit this thing that you care about, distant crossing objects, for instance, inside your BEV map, but you still want a representation for them. Well, now let's use an approach that doesn't scale with volume, but it scales with the number of objects that are in it.
Got it. So this two-stage architecture, I mean, are we talking about first stage, let's say, is like a occupancy network, and the second stage is these, let's say, is an object-focused of thing where they're just focusing on certain objects farther out to save compute space. So you get the occupancy network for things around you, but then the second stage is the objects that you think are important farther out. You're just focused on those objects without having to scale, right? This occupancy network in all directions.
Yeah, so I would say that the two-stage thing is probably, they have a stage that's still scaling as space. And, they've added another stage of evaluation of this stuff, which is specifically focused on objects and their movements. They specifically call this as a kinematics thing. So, if you're trying to evaluate if the relative velocity or if the velocities of distant objects are going to affect you, then I don't know. A good example, once again, this screams to me like it's a highway application, right? Where you want to look pretty far, like you're merging, you're driving on the freeway. We've all had, if you drive Autopilot, you get that situation where you're driving and you're in the rightmost lane and there's a big truck merging, right? And as a human, you're like, you would move over, right? Autopilot has to predict what that that truck's velocity along its path and whether it's going to intersect, right? And realize, oh, I'm going to be in that space. I need to either slow down or to be smooth, right? Or maybe I want to move over a lane. That's a prediction of a distant crossing object, right? It's a velocity prediction. But a lot of times in these situations where you're on the highway, you're going down the thing, the FSD, occupancy grid or the BEV map, it might not reach far enough out to include that truck, right? So right now they've got this blind spot where there are these distant objects that you want to be considering when you make your decisions right now about what you're going to do. But it's too expensive to just brute force expand the FSD map so that it's big enough that it can reach out a half mile to where that truck is. You can see it really clearly as a human being, and it's going to cross your path because you can see where the stuff is going. But FSD can't consider it in that basic mechanism. So they've got this other thing that they're layering on that can basically, it doesn't require it to fit inside the FSD, the BEV map or whatever. It can reach out to that object and make an estimate based on it, even if it's outside the grid.
Got it. Actually, let's do one more. This seems kind of important. The last release note update says improved geometry error of ego relevant lanes by 34% and crossing lanes by 21% with a full vector lanes neural network update. Information bottlenecks in this network architecture were eliminated by increasing the size of the per camera feature extractors, video modules, internals of the auto-regressive decoder, and by adding a hard attention mechanism which greatly improved the fine position of lanes. Okay. So, it seems like they made a update to the vector lanes neural network, improved this accuracy, and then through multiple means, they achieved that. Are there any notable kind of things here that you're noticing?
No, it's it's interesting that they had a bottleneck at the connection between the camera networks and so they made the feature descriptions that coming out of the per camera networks bigger, or rather the feature that ingests it into the BEV network or the occupancy network. They made it bigger so that it could ingest more features per camera. Yeah. It sounds like they did a number of optimizations and fairly straightforward improvements to the information that the vector lanes neural network got from the rest of the system, and then they got this numerical improvement in performance of 34% for ego lanes and 21%.
Yeah,
it's pretty straightforward.
Okay, yeah, it's just it feels like another just illustration that Tesla is doing anything and everything they can to improve their perception of and to create this 3D model that they're using to navigate the world through driving. So I'll just wrap up here. Thanks for sharing all of this. Oftentimes I feel after talking with you, I just get a better understanding of what's going on technically, especially under the hood. It's interesting to me that FSD is pushing ahead, and compared to where it was last year when we drove it in the summer, when we met up, compared to now, it's just mind-blowing, the improvements. And it's so interesting. You juxtapose that to a lot of the perception of skeptics and people who aren't following it. They just don't think Tesla's doing anything. They think it's just completely vaporware. Whereas Tesla is really heads down, I think, doing the right thing, improving. And it's not just one thing, that it's a multitude of things you need to improve to get this right. But they're really aggressively pushing forward. And it's super impressive. What are your kind of last thoughts with all this?
I'm happy with the progress. I'm glad to see that they're still moving. The biggest fear, and as long as this doesn't happen, eventually we get there. As long as you don't hit a local minimum, whatever, that you can't escape, like you hit a wall and stop making progress, you will eventually get there. We don't have a really good real world understanding of exactly how hard driving is, because we don't have an existence proof in a machine of something that can drive, where you can point at it and you can say, well, this is how hard the problem is. Yeah. It's this hard because this machine can do it. Because we don't actually know in those kinds of terms how hard the problem is, you can be very uncomfortable about whether you're or not you're going to get there. But, one simple fact is true. Like if you continue to make good progress, eventually you're going to get there. However hard it is, you're going to get there. And the progress is exponential. I mean, it doesn't feel exponential, but progress is exponential. Like they're describing all of these improvements as percentages against the previous version. And, that's exponential improvement. Like if you constantly make, same scale percentage wise improvements on your previous version, you're improving exponentially over time. And that means even if the problem is, exponentially harder than you think it is, but your improvement is at an exponential rate, then the amount of time it takes you to solve the problem is only linearly larger. It's not exponentially larger. Does that make sense? Mm-hmm, so sure. It's the difference between, it taking a year or 2 years to get there. It's not the difference between taking a year or 100 years to get there, right? And so that's very encouraging to me to see that they continue to make exponential progress against this problem.
Yeah, definitely. Good stuff. Right now I'm going to head out to Badlands National Park. Have you been there to Badlands before?
Yes, we did. It's funny, when we went, it was early enough that the supercharger network was I remember Badlands was the first place where that we took a trip in our car, and we looked at it and we're like, there's no supercharger there, which means we need to, have enough charge in the car to get out there, go around the park, and then come back to where we are, because there wasn't anything on the other side of it that we could. I don't think that's true anymore. But I remember this because we were really concerned about it. We'd never had to do that thing before. And then we went out to Badlands and we drove all the way around. We charged the car to 100%, drove out to Badlands. We met other people who had Teslas that were also there, so, and then we drove back and we ended up having like 40% charge left over. Like I was really impressed that the car did so much better than my expectations were. I think that was the last time I worried about range, actually. That was probably 2017. Yeah. It was fun. It's super pretty.
Yeah. So I'm impressed. I don't think I've ever been to South Dakota before this trip, and it's just been awesome. Yeah, it's been fun. And then we're headed to down to Colorado, spending a few weeks down there, the Rocky Mountain National Park and other places. So it should be fun. Yeah. Cool. Awesome, James. Thanks for taking the time to chat. I appreciate it for sure. I'm sure a lot of other people also will appreciate it. So have a great day. We'll talk to you again.
Take care. It was nice seeing you again.
All right.